ground? Could it bring somebody down if I never made a sound again? In your eyes, you've already spent my thighs, and you're rocking to the next big thing. Kissing the bride, 45 minutes aside. This was my dream, played out rocket routine. Who sucked out the feeling? Who sucked out the feeling? Where'd you go now that everybody knows that we did a couple shows out there? Look at me, I can write a melody, but I can't expect a soul to care. Kissing the bride, 45 minutes aside. This was my dream, played out rocket routine. Who sucked out the feeling? 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 Kissing the bride, 45 minutes aside. This was my dream, played out rocket routine. Who sucked out the feeling? 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 Who sucked out the
Okay, so we're going to continue with arrays this week, and we'll probably finish up with it today because Wednesday and Friday we'll probably devote that to tooling, which means that we'll cover the basic uses of a debugger, in our case GDB, and then we'll look at a really cool tool. It's a dynamic analysis tool called Valgrind. It'll be able to detect a lot of the things, especially in C, that go unnoticed, right? So a stack smashing event that doesn't result in a segmentation fault, it'll still be able to detect that and tell you something went wrong. And so you'll be able to analyze your code as it's running, which is why it's a dynamic analysis tool. But to finish up on arrays here, we need to talk a little bit about shallow versus deep copies. So let me come over here and I'll just go ahead and go with primes, right? And I'll go ahead and get rid of all this. It'll all be in your notes. I'll leave that, I guess, and just comment it out. Right? So what is a shallow copy? A shallow copy is when you have two references that point to the same memory location. So in this case, I've got one reference, primes, right? And it's pointing to this static array. Then what I can do is I can say int star b, and I can set it equal to primes. Now, the thing on the left-hand side, that is, let me make sure the audio works here. Yeah, the thing on the left-hand side, that is a pointer. But the thing on the right-hand side is also a pointer because it just happens to be a static array, right? It's still going to be a pointer to an integer array. Now, what happens when I make changes to one? Say primes sub 0 is equal to 42. Let's print out both of these things. So actually, I've got a function to do this for me, right? Print array, right? We wrote that, I think. Let's go ahead and do primes, and then there are n things in there. And then we'll repeat that with b, the second one, right? B. GCC demo.c. All right, and let's run this. Now you'll note that because I made changes to the first one, primes, the second one is also changed, right? That's because I've got two references, primes and b, pointing to the same thing. Because they're both pointing to the same thing, changes to one affect the other. Here's a pictorial version of it, right? That I've got A, which is referencing the original array, but then I make B equal to A, which references the same exact array in memory, okay? And so what I have here is a shallow copy, right? That's not always what you want. So what's the opposite of shallow? What's the antonym to that? Deep. What we want is a deep copy instead. So instead of creating a shallow copy like this, let's go ahead and create a deep copy. B will be equal to, now how do I create brand new memory? Memory that is completely separate from the original primes array. A call to malloc, right? I will typecast the return value there, right? And then I will say size of int times, and then in this case, 9, right? Now, have I actually copied over the values 2, 3, 5, 7, etc.? Have I copied those over? No. So I need to do that manually now. For int I equals 0, I is less than n, I plus plus, b sub I will be equal to prime sub I. Okay? Now, once I've copied it, changes to one do not affect the other. So let me show you that. By moving that change code down here, right? Primes, I'll change the first prime to 42. But now, will that change B here? Probably not, because it is a completely different copy, right? The original 2 is still in there. I only change, or the copy of the original 2 is still in there, right? Here is that same deep copy, or that same diagram here, but it's a deep copy. A is referring to its own memory, B is referring to its own memory. They happen to have the same contents, but they are different memory locations, okay? So that is the difference between a shallow and a deep copy, right? We'll come back to this here in a second and formalize that. But a shallow copy is when two references, pointers, point to the same chunk of memory. Changes to one affect the other, right? Because they're the same thing in memory. There is only one thing in memory. Right? Now, a deep copy is when there are two separate arrays that have the same contents. Right? These are not the same thing in memory. These are two distinct things in memory. Changes to one do not affect the other. And this is important because if you want to give off your array to a function for data processing or something like that, and you know that that function is going to make changes to your data, right? Because there is no const in front of it. That means what you have to do is you have to create an original copy if you want the original retained. Make a copy, then hand that off to the function for processing, and you'll retain the original copy there. So let's go ahead and do a demo here. Write a function to do this. Right? So we're going to write a function to do this for us, right? And then we're going to improve that function. Okay. Basically, what I want is this chunk of code right here, but I want to put it into a function because that seems like a pretty good piece of functionality to have, right? So I will return an array, which is int star. I'll call this deep copy. Right? Okay. And I will have const int star array because I'm not going to be making changes to the original array. Right? I'm going to make a copy and give it to you. Sometimes these are called clones. Right? I'm going to clone it, and the clone is a distinct person, right? And I'm going to return it. Right? Int n. Now, do I need to communicate the size of the new array? If it's a copy, no, right? Because you told me that it was of size n. The result is going to be of size n. So, document it. Creates a new deep copy of the given array, or creates and returns a new deep copy of the given array of n integers. Okay. All right, there's my code. Where's my, there we go. There's my signature. Okay. So instead of calling it B, I'll call it, say, copy, right? Copy. Right. Oh, actually, I don't want that at all. I'll say copy is equal to int star size of blah, blah, blah. And then copy should be array, ARR, of that. And then return the copy. Once again, what did I forget? Error handling, right? So how should I error handle this kind of stuff? If you gave me an array that was null, what would you expect as a copy of that thing? Return null. That's the only thing that you can return because you are returning a pointer, right? If your n is less than, if your n is, now if it's 0, we've already agreed that that's okay, right? Go ahead and create a 0 copy array. Right? But if n is, say, less than 0, then yeah, I'm also going to return null because null is the only thing you can return when your return type is a pointer like this, okay? Cool. Now I can use this in my original main up here, right? There we go. So I will make a copy, a deep copy of primes and n, or n, not 9. Don't hard code it like that. Now I don't need this stuff, and so changes to 1 do not affect the other. GCC, oops. Where did I screw up? That's good. That's all good. And then down at the bottom here, where did I screw up? I probably have... Oh, no, I don't see any screw up. Do you? All right, fine. We're going to have to read. I hate reading. All right, so expected declaration before malloc. Oh, yeah. So what's the issue? An equal sign. There we go. And then all the rest of it is just error following that one error, right? There we go, a dot out, and you'll see that it's still a deep copy because changes to the copy or the original don't affect the copy. Right? How would we do, here, let's improve this actually a little bit. Because what you're gonna end up doing is you're gonna end up creating a deep copy for integers. If you want one for doubles, you're gonna have to call it double, right? If you want one for eventually strings, you'll have to call it char or str or something like that, right? So here's a slightly better improvement of this. There is actually a built-in deep copy function. It's not what you would think it looks like. It's called memcpy, right? Now, what do you think mem stands for? Memory, and cpy is copy, right? So memcpy c.man page, right? So I think that there are two arguments to this. Let's find out what they are. Let's see, where is it? All right, so there's the size. There is the destination. There's the source. Okay, there's only 3, it looks like. I don't know why they put it like that with a semicolon. Is there a better man page than this? Let's go with this, Linux documentation. That's going to be better. There we go. That's a little bit better. And for some reason, it's in the string library, which is a preview of what we'll do here. I find that hard to believe, but all right, so be it. memcpy, the destination, the source, and then the end here. Be careful, though. The function copies n bytes from memory area source to memory area destination. The memory areas must not overlap. If they do, that'll be a segmentation fault or something. Implicitly, what does that mean about the destination? And note here the order, the destination, then the source. Why? Because it follows that equals, that assignment operator. You take the thing on the right-hand side and you put it into the thing on the left-hand side. So what is the underlying assumption here about this destination? It's not going to create memory for you. It should be big enough to hold whatever that is, right? So let me show you what it would look like if we modified our function down here. Where is it? Let's see. We would still have to call malloc, but we don't have to go into this for loop and copy over each 4 bytes, 4 bytes, 4 bytes, 4 bytes. What we could do is we could call memcpy, and the destination in this case will be the copy, the source will be the array, and we will end up copying n things. So I'm going to go ahead and get rid of my original for loop there. And it will work just as before, except that, yeah, it is definitely in the string library for some reason. Right? So let's go ahead and bring that in. Include string.h. That's something that we'll talk about after the break. Oops. GCC, there we go. And let's run it, and you'll see that it's exactly the same as before. Oh, sorry. So if we run Valgrind, eventually we'll find out why this is. But remember, what is n in this case? There are 9 primes in that thing, right? So it's 9. But what does the documentation say about copying? It copies over n bytes. So it copies over only n bytes. In other words, the first 2 values and then half of the second, or like a fourth of the third value there. And that's why you're getting something that looks like this, all right? And then the rest of it's not copied. So what should I actually be putting here? Size of int times n. That's how many bytes you allocated. That's how many bytes are in the original array, and that's how many bytes you need to copy over. There we go. All right. So I'll go ahead and leave that in there, but you may or may not use it. Use it if you want to. Just you got to be sure about how to use it. Ultimately, though, there's still going to be a deep copy for integers. There's still going to be a deep copy for doubles, et cetera, et cetera. And also, you end up having to call malloc yourself anyway. So it doesn't really save you that much code here. Right? Although this is internally, this is going to be way more efficient because it's going to be able to copy a chunk of memory at a time instead of 4 bytes, 4 bytes, 4 bytes, 4 bytes. Okay. All right, let's talk about Java here really quickly. Right? I also want my primes. So where are my primes? Primes. There we go. Okay. Now remember we said that we're immediately going to get away from arrays like this, but let's go ahead and look at it with respect to arrays. Then we'll look at it with respect to lists and sets and maps and stuff. All right. So how would you do a deep copy here? Well, you could write a function if you really wanted to. Right? I don't want to write a function though. Right? There are these things called helper or utility functions in the array class. Copy of. Arrays, excuse me, dot copy of. Right? And there are several of them. There's a version for booleans, for bytes, characters, doubles, floats, integers is what I want. Right? So I want a copy of primes. Well, what the heck is that second one there? Right? And that's going to return an int copy. Right? I'll just call it that. Right? That 0 there, or that number there, that's the size. Now, wait a second. I thought in Java the size was maintained in that dot length. This is actually a size that allows you to grow it or shrink it if you want to. So if I do the original, primes.length, right, then that means that it's a straight up copy of the original. Let me go ahead and print them both out. System.out.println primes. Oh, this is a good exercise actually. And copy. Just guess what you think it's going to output here. It's not going to look good. Gobbledygook, right? What is that actually? It's a memory address, right? Now we don't have pointers in Java, right? But the Java virtual machine still manages memory. And so the default value here that it's going to print out is just the Java virtual machine memory address here. How do we get something meaningful? Well, we could go back to C and copy and paste that print array, right? Remember, we could go ahead and do that. But I don't want to do that either because I don't like writing code. So I'm going to once again rely on this thing that somebody else has already written, arrays.toString. And there are many versions of this, but if I go primes and copy, then I don't have to do any work, right? It automatically formats that as a nice looking string, and then again changes to 1 do not affect the other. So I don't know, primes of 0 is equal to 42. I'll show you that it's affected by the first one, but not the second one, because it's a deep copy. But it doesn't just stop there. You can make copies. Copy 2. Here, I'll just reuse it here. Right? If you want to, you can go ahead and add 10 to the length. What does that do? It copies over everything, but then because you said plus 10, it'll fill it out with zeros on the back end. Right? What if you wanted... it's not minus 10, but minus 5, right? So actually, I'll just put in 5. Right, there we go. That's easier to understand. Right? What that's going to do is that's only going to copy the first 5 things in the array. Right? So this extra parameter allows you to expand or contract the new array. It doesn't do anything to the original array, right? Because you can't change those. Once they're created of a certain size, that's it. That you're done. Right? How do we do the same thing with lists? List. Evens. So integer. Right? Evens is equal to list dot of. Here's a really quick, new array list of, can I do this? 2, 4, 6, 8, 10. I don't think I can do this, but I could do this. Nope. This. Come on. There we go. No, I can't do that either. Right? All right, fine. I'll just add new evens add 2 evens add 4, 6, and 8. There. There's an easier way to do this, but I was about to use list.of, but what that actually does is it creates an immutable list. You can't change it, and I want to change it, right? Because I want to demonstrate this here. All right, so I've got 4 things in there, right? I can say list of integer evens copy is equal to new array list. And what I can do is I can add a parameter inside of this parentheses here. This is called a copy constructor, right? So these are actually called constructors. We'll talk about those later on. They're a way to construct an object, in this case a list. But a copy constructor takes another instance of a list and copies everything in that list over to this list. So that if you make changes, say evens copy.add 5, something that's not even, right? And then I try to print these both out, system.out.println evens and the copy, you'll see that only the copy is affected here. Right? 5 was only added to the original because it is a deep copy. All you have to do is provide this as an argument in the constructor when you create it. Same thing with lists, same thing with maps. Okay? So there is our demonstration on deep versus shallow. I'll wait for the C to just copy and paste everything because it's all one big blob right now. All right? The last item, though, that we need to talk about with respect to arrays are multidimensional arrays. Right? So what are multidimensional arrays? Well, a dimension is, a direction, right? The x and the y axis, so you've got 2 dimensions. Well, the regular old arrays that we've been working with, they're all one-dimensional arrays because they run in one direction, right? You can have 2D arrays, right? 2D arrays have rows and columns, right? In what situations have you seen such things? In real life or in other endeavors? You've got things with rows and things with columns. What do you call those things? Tables, right? Right? Tables have rows and columns. Or maybe a spreadsheet, like Excel, right? Or, if you want to think more mathematically oriented, linear algebra, matrices, right? So, lots of different applications here. Yes, you can have 3D, 4D, etc. arrays, but likely there is a better solution, right? So, yeah, you can have 3D arrays, 4D arrays. Once you get to 4D arrays, though, we're past our existence, right? Because we are 3-dimensional beings, right? And what does it look like, right? Well, you can't visualize it anymore. At least with 3D arrays, it's kind of like a box, and you've got grids in the box. But again, there's probably a better solution. That better solution is probably going to be a class in Java or a structure in C. That we'll talk about those later on, right? So we're going to stick with 1D arrays and 2D arrays. In C and in Java, you can specify 2 indices. That is, if I've got a table, it's ij. This is going to refer to a column I, or row I and column j. This is what's called row major form instead of column major form. I don't even think the weirdest linear algebraists out there would use column major form, or they do the column first and then the row second. I don't know why they would do that. But anyway, So what we're going to do to set up memory in C is we're going to have an array of pointers. Right? Why? Because each pointer will point to a row that is 1D array of, say, integers, right? Or doubles or whatever you want. Right? So we're going to have to set up an entire column of pointers, and then each pointer is going to end up pointing to a row. Let me show you how to do it over here in the demo. Let's go back to our main, and I'll get rid of all of this stuff here and work down below. There we go. All right. You still need to do all your bookkeeping. So in this case, if you want to keep track of the number of columns, right, then you'd use n. We'll go ahead and go, or rows, excuse me, row major form. And then if you want to keep track of the number of columns, just create another variable there, say 5. Okay? Now, to create an integer array of 2 dimensions, guess what you do? You have 2 pointers table. Right? All right, so how do you set it up? Well, we're going to set up an array of pointers. I'll show you what this looks like here in a moment to visualize it. But otherwise, what I need to do is I need to set up that array of pointers. Right? Int star star. Right? Why? Because, well, what is table? It's an int star star. It's going to be a call to malloc, but now how many bytes do you actually want? If this were a 1D array, I would say size of int times n, right? But it's not a 1D array. How many bytes does each pointer in that array take? Int star. There. Now that only sets up my array of pointers. It doesn't set up all my rows, okay? What I need to do now is go into a for loop. And for each pointer in that array, I is less than n, I plus plus, I need to allocate that array. Now, this is what we've been doing up till now. This is just going to be straightforward. Table sub I is equal to a call to malloc, and how big? Size of, now it's just regular old integers, times, now be careful, how many of them do you want in each row? You don't want n rows, you want m columns in that row, right? So m, there we go, space, there we go, okay? Now after you've done that, you can go ahead and use the double indexing. Table sub 0, 0 is equal, 0, 0 is equal to 42. What is the last one? If I go 123, what is the one at the bottom? Last row, last column. What's that going to be? So the last row will be at n. Careful. We start at 0, so n minus 1. What about the column? Same pattern there, m minus 1. Right? Now let me visualize this over here in Python Tutor. Right? Visualize this execution as we go through it. Right? There we go. So n and m are initialized to 3 by 5. We're going to have a 3 by 5 array. That is 3 rows, 5 columns. Right? That first one, that first call to malloc is going to set up our array of pointers. Right? The first one is a pointer to an integer, pointer to an integer, pointer to an integer. These are not integers. Right? Each iteration of this for loop is going to set up each one of those pointers. So the first one points to the first row. The second one is going to end up pointing to the second row. The third one is going to end up pointing to the third row. Right? And then after that, you can go ahead and set the values. That top leftmost point is going to be 42, and then the bottom right is going to be 123, and then everything in between. Right? Whatever you want to do with it. Next week, or this week, I guess, since you're getting to do arrays, you're going to use 2D arrays to do image processing. Why? What is an image? It's a 2D array of pixels, right? And a pixel is an RGB value, which you've already been working with. Right? So you're going to do a bunch of things like flipping it horizontally, flipping it vertically, rotating it, and stuff like that, instead of the sepia stuff. But what do we do when we want to get rid of this stuff? Let me come over here and let me propose an idea here. Remember that we've got to clean up after ourselves. So after you're done using something, what do you do to give it back to the operating system? Free. What if I just freed the table? Right? Let's visualize what this looks like. Right? I'm going to fast forward, since we already saw it. Right? All right, what's about to happen on line 16? What am I actually freeing here? What is this pointing to? It's pointing to this array right here of 3 pointers. When I do that, what happens to these 3 arrays down here? Yeah, they're still there. They get leaked out, and there's no way to reach them because I deleted all my pointers to them. Right? It's not going to visualize it nicely here, but there's definitely a memory leak. Okay? So let's come back over here and rethink this. If you're going to destroy something, you need to, or if you erect a building, I guess you could just blow it up, right? That's what they building implosion. You just destroy it all at once. But generally, what you want to do is you want to take it down floor by floor by floor. If you put it up floor 1, floor 2, floor 3, floor 4, then what order do you take it down in? 4, 3, 2, 1. So that's what you have to do. You have to deconstruct this by first freeing up each one of those arrays. For int I equals 0, I is less than n. It doesn't matter if we go forward or backwards on this. I can free table sub I, the ith row. Then after I'm done, I can free the table. Okay? That's the proper way of cleaning up a 2D array, at least the way that I've built it here. All right? There. So let's visualize this. And once again, we get down to line 14. There we go. Now what we're going to do is we're going to start freeing up each one of those rows. The first row gets freed up first, right? Second row gets freed up second, third row third. Now we are free to free up the pointers to the pointers, and we can clean up after ourselves properly. Okay? All right, so once again, I'll put this in the notes. Actually, no, now I'm done with C, so I'll put this all into the notes. Okay? So C, there we go. What about Java multi-dimensional arrays? All right. So let's come back over here to Java, and I'll go ahead and I put that in there already. All right. So first of all, can you get by with using lists? All right. I want a list of, well, what will be in that list? If it's 2D array, if it's a 2-dimensional thing, a list of lists of integers, right? Yes, you can do that, right? Table or something like that, right? You'd have to go through and you'd have to initialize that list of lists. Then you'd have to go through and initialize each list, right? Yeah, all right. Not only that, but you're no longer guaranteed that each list is of the same size. So the first list could end up being 5. You add 5 things to it. The second list could be of size 2. The third list could be of size 50, right? That's not what I want, right? What I want is uniformity here. I want the same number of rows and the same number of columns. So what I can do is I can do it all in one line if I use regular old arrays. Table is equal to new int of 3 by 5. Oops, sorry, 5. Right there, that's it. Right. Now it's guaranteed that it has 3 rows and 5 columns in each row. How do we go about setting stuff? For int I equals 0 is less than. Now I could put that 3 into an n and that 5 into an m, right? And just use those variables, but that's not the Java way. Those are being stored in the table itself, table.length. That gets me the number of rows, I++. Right? Then for int j, for each column in there, j is equal to 0, j is less than table. Now I can't go length here because remember that's 3. I'd be treating it like a square matrix all the time, 3 by 3, 5 by 5. So what I need to ask is, well, in this particular row, how many things are there? Right? And there's the length, j++. And then I can set those values, I don't know, table of I, j is equal to I plus j, or I times 10 plus j. It doesn't matter. You're just playing around with it. Now, do you need to free it up here? This is Java. Memory management is taken care of for us. There is no free, right? Once you're done using it, Java will detect it automatically and then make it eligible for garbage collection. Right? So that's how you can create it. You let Java destroy it for you. How would you end up printing it? So is there an arrays.print 2D array? No, unfortunately not. So this is a case where you're going to have to do it manually. For int I equals 0, I is less than n, or n not len, table.length, I plus plus. Now remember that each row is an array basically. So I could use system.out.println arrays.toString of table sub I. Right? I don't have to write the entire piece of code, right? And there we go. It's not going to look nice because it's not going to align everything up, but who cares? Right? If you need it to look pretty and nice, then you're going to have to write your own code to do it. Right? All right. So, any questions on multidimensional arrays? Again, you can have you can have whatever you want. You could have a list of lists of integers. You could have a list of set of integers. You could have a set of list of integers. Right? You could do whatever you want. You can parameterize this to whatever you want. You could have a map of sets or something, right? In fact, that's actually useful, right? That other stuff is kind of why would you do that? But a map, say, of integers mapping to a list of persons, right? If you had a person class of some sort, right? And then that's an ID that maps to groups or something, right? Like a class or something. In fact, let's do a string, right? That would map CSCE 155H to a list or set of persons that are enrolled in that course, right? So yeah, that does get very, very useful to use collections within collections when you've got a map, okay? But if you just want a 2x2 or a two-dimensional array of things, you're probably going to want to go with the traditional array here. Okay. All right. Nothing else? So, demo, Java. No questions? All right, so then I have a question. When is has anybody successfully gotten stuff into CodePost since Friday? No? No? Okay. So we're going to probably go into emergency mode here and use a backup system. Unless they get it fixed in the next 24 hours. I've put in a ticket to set it up, and then I'll furiously be setting it up this afternoon. And if it comes to it, then we'll use that, and then hopefully go back to CodePost when they get stuff fixed. All right. Yeah, go ahead.
How would we turn something in there?
That's the backup system. There's a hand-in system and a web grader that I wrote that I've used in years past. And then the reason that I switched over to 100% CodePost 2 years ago was because they were stealing our server away, and they were doing it the week before classes started. And so I said, screw this, I can't rely on you guys. This is ITS, not our guys. So I went to CodePost fully, and I've used that for CS1 since then. And I still use our hand-in system for CS2 because CodePost does not, in fact, CodePost, Gradescope, Turing, whatever else you're using, they don't handle database stuff very well. So we'll still be using it. The system, the backup system, we'll be using that next semester.
What if we just post it on campus?
Well, CampusWire, I'll put up a notice on how to get into it. You use your same login, and I'll send out the URLs for it. Again, hopefully they fix it. It still wasn't fixed this morning for me, at least. All right, then I'll see you. Again, it was longer term here. We've got a full week of class this week. Then you've got Monday and Tuesday off next week. Wednesday will be a review. We'll bring in the last midterm. And then Friday will be your exam 2. All right. Everything up to and including today.